Okay, Assalamualaikum and very good day to all of you. So we continue with this video for the discussion on the examples for the unbalanced three-phase system, and then the three-phase power calculation, and also two watt meter method for calculating for reading of the three-phase system. So we begin with example 2 from our slide. So a three-phase four-wire unbalanced load. Okay, so three-phase four-wire. So you should know four-wire meaning that it has what we call the neutral cables. Okay, so and this question is said that the load is unbalanced load. Okay, but it is supplied by a balanced three-phase voltage supply, which is 220 volt. This one is V phase and it is in positive sequence. The impedance per phase as follows. So as you can see, obviously they are not balanced. And it also said that use VAN as a reference, okay, where the angle is negative 30 degrees. So the question is find the line current and neutral current. The second question, construct the Phasor diagram. Okay, so the information that we have is actually the impedance and also the V phase. Okay, so V phase, as usual, we need to it's very easy. It's actually to write down all the values of the V phase. So 220 volt with an angle of negative 30. So this is our reference. Okay. And for VBC, so since this is a balanced system for the voltage source, so the magnitude is the same, but the angle must be 120 degrees difference from the VAN. Okay, so that's why we have negative 150 degrees, and also for VCA 220 with an angle of 90 degrees. Okay, so right now, as you can see, we have already obtained VAN, VBN, and VCN. And from that, we know that VAN is the voltage across this impedance of ZAN. So from that, we can calculate directly your IA. So IA is actually VAN over ZAN. Okay, so together with IB, so this one is actually VBN over ZBN, and IC is actually VCN over ZCN. Okay, so finally we obtain the values of IA, IB, and IC. Okay, and from that you need to construct the Phasor diagram. So Phasor diagram, I think, is very easy and straightforward, and I think you have no problem on that. Okay, let's move on example 3. So I think example 3 is also the things is really the same. So I think I can skip, but I will share with you this solution for your reference. Okay, so we move to example 4. So example 4 is quite looks like it's very tough, but it's actually, if you read carefully, it is actually a straightforward questions. Okay, so let's try to look at the solution. So a three-phase Y connected load is supplied by a three-phase source, which is a balanced three-phase source, 346.4 volts with a 50 hertz. The magnitude of the line current are given, which is IA is 50 amperes, IB is 40 amperes, and IC is 33.33 amperes. By using a Phasor diagram in figure 1 here, calculate the each load impedance value. So the question is to find the load impedance value for each phase. And choose phase A, voltage as the reference, and the source is actually in a positive sequence, meaning that it is A, B, C. Okay, so the information that we get is actually the current values and also the angle of the current. Okay, so this is a Y load connected, meaning that I phase is I line. Okay, so from the phasor here, you can see that directly you can get your IC is with an angle of 30 degrees. IA is actually 0 degrees and IB is negative 30 degrees. Okay. So this is actually the full diagram system that actually represent these questions. Okay, so as you can see, we have VAN here, and then the current IA, VBN, and also VCN. Okay, so right now we have already all the information here. Okay. And also right now, VAN is equals to the voltage source, which is 346.4. So from that, we can directly calculate your impedance. Okay, because VAN is already known. Okay, IA is also already known. So we can get the impedance of phase A, 6.9 ohms, ZB, and also ZC. So as you can see, it is straightforward. The main problem is to understand the diagram of this phasor diagram. And also to understand the question. Okay. Okay, so let's move on. Example 5. So example 5, I think is quite consume a lot of time, okay, because you have what you call to use a mesh current. Okay, this is one is referring to our nodes where the system is unbalanced. Okay, the load is unbalanced, but you don't have the neutral cable. So neutral cable right now is actually has been taken out or maybe damaged or so on. So you need to calculate what is the current and so on. Okay, and also the voltage. So as you can see here, we are no longer referring this node as an N because we don't have neutral cable. So this is referring to the what we call just a point here S. So we have the impedance, which is ZAS, ZBS, and also ZCS. And it is connected Y connection, and it is supplied by a Y connected balanced voltage supply with a line voltage of 415 volt. Okay, 415 volt. So if the sequence is positive and VAB as a reference, so find these parameters values. So firstly, what you need to do is actually to write down the values of the line voltage. So VAB as a reference, so meaning that the angle is 0, VBC, and also VCA. Okay. So we need to write down like this because it is a positive sequence. So VAV, VBC, and also VCA. And then after that, you have already got all the information. So all the voltage is known. The impedance value is also known. Then you can actually draw or analyze the circuit by using the mesh analysis. So right now we have two loops. So you can just use I1 and I2. Okay, so from here we can get the equation for mesh current 1 and mesh current 2. But as you can see, it involves a lot of time because you are dealing with complex numbers here. Okay, because ZA is a complex numbers. So you have two variables unknown, which is I1 and I2. So you need to have two loops only. Okay, so after you obtain by using your calculator I1 and I2, So you can get your IA, IB, and IC by using this information. We know that IA is a straightforward is equals to I1, while IB is actually equals to I2 minus I1, while IC is actually negative I2. Okay, so sorry, this one is actually negative I2. Okay. So, and then after you obtain the IA, IB, and IC, then you will directly obtain your what you call the load, okay, the voltage across the load, okay, and also you can sketch the phasor diagram. Okay, I think that is for the unbalanced three-phase examples. Next, we go for example 6. So this one is actually example for a three-phase power calculation. So this example is shown here where the load is connected in Y connection, and it is a balanced system with the impedance for each phase is given 70.7, angle negative 40, negative 45. Okay, so meaning that negative 45, meaning that your load is actually a capacitive load. Okay, and the load is connected to a source, three-phase source, 416 volt. Okay, positive phase sequence, and VAB as a reference. So since it didn't actually, this 416 is actually a V line. Okay, so 416 is actually your V line. Please be noted that if for the question, it should be the values here, for example, 416, okay, should be given. What is the variable? Is it referring to V phase or V line? Okay, so I think this question is not complete, but for your information, this one 416 is actually your V line. Should be stated there. Okay, never mind. So so your VAB as a reference. So the angle is 0. So this is positive sequence, meaning that VBC and BCA. Okay. And to get the IA here, okay, IA is actually you can get by having the VAN, okay, because this one is your ZA. So VAN over ZA. So what you need to do is actually to convert the line voltage here into your V phase. Okay, so for example, like this, we have already calculated it. Okay. Okay. Why I give negative 30 degrees? Because we know that V phase is actually behind the V line. Okay, so V line is right now 0, so meaning that your V phase should be 30 degrees behind 0, which is negative 30. Okay, so and divided by your impedance, so you will obtain your IA as this one, and IB also. So the angle, okay, so for the phase voltage, you need to minus 30 degrees. So that's why we have negative 150 degrees over your Z. So you will obtain these values. Okay, and I see also this one. So since this is a load, balance load, you can see the current is actually the same. Only the phase is different, which is between IA, IB, and C, the difference should be 120 degrees. Okay, and then if you use these equations where I n here should be 0, okay, because for the balance system, the current that flow inside the neutral cable should be 0. Okay, so if you calculate the current IN is not equal to 0, meaning that there are something wrong in your calculation. Okay, so this is the phasor diagram. Okay, and then the next question is the total active and reactive power absorbed by the load. So this is a three-phase system. So we can either use, there are two equations you can use, whether to use V phase and I phase or V line and I line. So in this case, I use V line and I line. So you need to multiply with square root 3, multiply with the cos of the different angle of between the voltage and also the current. So the voltage and current difference is actually, we can refer to the impedance, okay, which is 15 degrees, okay, 15 degrees. Sorry, not 15 degrees. Okay. Okay, based on, I have do a correction. Okay, so for the real power, so you can use a V line and I line, multiply with square root 3, and the voltage, the theta voltage and theta I here, you should use V phase, okay, V phase. So this one is V phase and I phase. So based on our calculation, the V phase is actually negative 30 degrees. Okay, and the current I phase, which is also your I line, is for 15 degrees. So the total is actually negative 45. So cos negative 45 is actually, so this is incorrect. This is incorrect. So I need to do the calculation first. Okay. So after do the calculations, the total power is 1732 watt, while the total reactive power is negative 1732 var. Okay, why negative? Because it is a capacitive. Okay, and if you put the sign negative 45 also, you will obtain the negative values. The next question is the total apparent power by the power source. So you just use the S supply, which is the apparent power supply, which is the V line of the voltage supply, and also the current line, which is 2, and then you just multiply with square root 3, which is this one. V line is 416, and the I line is actually 3.4. Okay, so this one is actually 2449 VA, and the power factors is, you can actually use this one. Okay, so I need to double check this one. It should be different from the original, from the answer here. Okay, so the total power factor is just use this one, which is cos negative 45 degrees, which is 0.707 leading. Okay. Okay, I think that's all for the calculation for the three-phase power example. Next, we go for the example 8, which is a 2-watt meter method. Okay, so for three-phase system, there are two ways on how we can measure the power for the three-phase system. The first one is by using 3-watt meter method, where all phases are connected with a one unit power meter. And the other method is actually just by using, instead of using 3, we are using 2-watt meter. Okay, so but this one is only applicable if the load is actually balanced. Okay. Okay, so example 8. A balanced wire connected load is supplied from a symmetrical three-phase 440 volt 50 Hertz supply system and positive sequence. The current in each phase is 20 amperes and lag behind each phase voltage by an angle of 40 degrees. And please use VAN as the reference and calculate the followings. Okay, so right now the information given is actually the V line, which is 440 volt RMS. So so for the Y connection, so V line is not equals to V phase. So what you need to do is to convert the V line into V phase and use that V phase VAN as the reference. So as you can see, we have calculated it, and the angle is set as 0. And after that, you can get the VBN and also your VCN. Okay. And so we have finished answering the phase voltage questions. The next is the load parameters. So for the load parameters is very straightforward. Is VP over IP. So your VP is given here, and your IP is actually your I line. So 20, and then the angle is negative 40 degrees behind. So we have the ZP is equal to 9.7 plus J 8.2. So this one is actually inductive load. Okay, and then the total power based on the equation. So you can use either V phase, I phase, or V line and I line. So in these examples, I use V line and I line. Okay, and multiply with square root 3, and then multiply with the power factors. Okay, so we get the answer is around 11.676 kilowatt. Okay, that is the total power for three phase. And the last question is actually what is the reading of each wattmeter? So wattmeter number 1 and wattmeter number 2. So this one is by referring to the notes, okay, that I have revised. Okay, so the P1 is actually the reading of your VAB and also your IA. Okay, and then multiply with the cos theta plus 30 degrees. Okay, this theta is actually your different angle between V phase and I phase. Okay, so this one 40 and plus 30 degrees, so you will obtain this one is equal to 3009 watt. And for a reading of your P2 is actually reading for VBC and IC. Okay, cos theta minus 30 degrees. So you will obtain the reading of P2 is 8666. Okay, so if you sum up this one, okay, you will actually obtain the same answer, which is 11.67 kilowatt, which is equals to the reading, the calculation that we use to calculate the total power. Okay, meaning that your calculation, the reading is actually correct. Okay, I think that's all for the discussion on the examples for the unbalanced system, three-phase power calculations, and also the 2 wattmeter method. Okay, thank you very much and have a nice day.